Hello everyone, Dr. Shane back with you. So we are moving into the section of chapter 12 on chemical kinetics where are looking at specific types of problems. So this unit and the next unit, you're going to want to get very good at reading a problem and identifying it as a specific type of problem, and then so you know where to go, because sometimes on paper all these problems kind of look the same. Not really, but that's where you want to get going. So this first type of problem that we're doing is called the method of initial rates. Remember what an initial rate is. It's the tangent of the line at time equals 0. Now you're going to be given data. You're going to be given concentration data and rate data. So you'll be given what's the initial rate when the concentration of the chemicals are some fixed value. And then you're expected to handle that and then come up with a mathematical expression that describes the chemical equation. That is called a rate law. So you can copy all this down while you're listening to me. So this is subheading 3, is we're looking at mathematical models, mathematical equations that describe chemical kinetics. And the first one is called a differential rate law. So, and then we're going to do something else called an integrated rate law. So I might as well explain this right now. I was going to do this on the next slide, but might as well do it here since there's space. Differential, what does that mean? Well, that means we are defining a mathematical equation that is based on the change in concentration over change in time. And that's a rate, okay? Well, that's one way of expressing the rate of a chemical reaction. That's actually the only way. And we are going to come up with a mathematical formula. So that's rate. And this one, let's assume you only have one reactant. So it's like decomposition or something like that. So it's A turning into B plus C. That doesn't really matter for now. So that's the rate. And we are going to come up with a mathematical expression. Well, okay, first things first. The rate is proportional to the concentration. That probably makes sense, is that in some way, shape, or form, the rate depends on how much of the chemical is there. We talked about collision theory, but it's not quite that simple. It's not always a one-to-one. It's not like if I double the concentration, I double the rate. That does happen all the time, by the way, but it's proportional. But to make it equal, this is just a preview of coming attractions. So we introduce this lowercase k, which guess what that stands for? Constant, called a rate constant, times the concentration raised to some power. And that power is called the order of reaction with respect to chemical A. When we have more than one reactant, we'll have more than one order. Chemical A, chemical B, chemical C. I don't think we're ever going to consider more than 3. That gets too hairy. So 1 or 2 is pretty typical. So that's where we're headed. This is called a differential rate law. And how does the rate relate to concentration? So this is subset number 1. And I guess I can leave those notes there. Let's see what other notes we have to take. And then I'm going to do 2 examples, one thoroughly, and then we'll save it for the rest of the class, because you don't really want to sit here and watch problem after problem. Okay, so we'll look at, you can probably read this through here. We'll look at hydrogen peroxide decomposition, because actually we already have that data. We're going to look at one from the book. I guess I can erase all of this now. This is one taken right from the book. It's another decomposition of a molecule called acetaldehyde. And that's the one I'll use as an exemplar. And then we're going to do a more complex one in class, because this video is going to be like 2 hours long if I do every possible example. And then we'll, maybe in class, or you can do this one. There's an example that's a little more complicated. It's also it's one that has environmental applications, is atmospheric ozone depletion. Again, one from your book. So you don't need to, if you don't like to watch these videos, you want to take a break, go look at the book. Okay, so what do you do? How do you approach these problems? I'm going to illustrate all of this. So what you do, all right, I already said that. There's 2 different ways to determine, oh, by the way, what I showed you before was called an example of a rate law. So in this case, a rate law, the differential rate law, is the rate equals some rate constant times chemical A raised to its order, well, oops, I guess that would be N, that comes before M, times B raised to another order, so that'll be N, M, and then if we have C, D, E, F reactants, these are just for the reactants, by the way. That's what we're determining here. We're determining the rate law. We want to determine the order. That's what it means. What are these? Oh, by the way, order is going to be an integer, either 0, 1, or 2, and then we add them all up to get the overall order. That's just a preview of coming attractions. So those are integer values, and the rate constant is just something we calculate afterwards. I think you'll see how this all fits together. So there's two ways to do it, and I'm going to show you the first way here. Well, both ways, actually, of this subset. So take a look at the data and figure out what the orders of reaction are just by inspection. That's a fancy way for saying just look at it and figure out the proportionality. And there's one where you actually go through the math to figure them out. I'm going to show both ways here. All right, here we go. Let's look at one we've already done before. So these are examples of differential rate laws using the method of initial rates. Again, that's really important. So this is example number 1, H2O2 decomposition. And I think you had this data before. We actually used some data from the introductory part where we calculated initial rates or something like that. It doesn't really matter. This is just, assume this is data that you're given. And I believe here we had 2 trials. We had trials 1 and 2. And the concentration of H2O2. Now I'm going to be explicit about this. This is the initial concentration. That's what the subscript 0 means, the concentration at time 0. So in other words, you go in the lab, mix up a solution, well, and that's the initial concentration before the reaction takes place. And let's just keep it simple, use molarity. And you would be given these. We calculated some average rates before, just by taking data that I gave you. And these are the initial rates. I kind of ran out of room. So these are the rates at time 0, and the units are molarity per hour. Now this is not perfectly consistent with what we did before, but for purposes here, it doesn't matter. And we're just going to look at 2 trials. I think we did 3 trials before where it was the concentration was 1, and then it was 0.5, and then it was 0.250. We're just making the point here. This is a setup for a slightly more complicated example. And we did the initial rate, or the rates that we came up with before. I'm just going to rewrite these. Were 0.0831 and 0.0418. So in other words, about half. Doesn't this look easy? Because we cut the concentration in half, and the initial rate goes down by half. So it's like a 1-to-1 proportion. Well, guess what? That's exactly what it is. So what we're trying to do is come up with a differential rate law. And in this case, the generic form is that rate is somehow proportional to, well, what's the reactant here? Not just some generic A. Well, the rate is proportional to H2O2. And to make this an equality, rate equals the rate constant times H2O2 raised to some power, which we call the order of reaction. In this case, it is both the overall order, because there's only one reactant, and the order with respect to hydrogen peroxide. There's only one reactant. So this is the order of reaction, or it's actually better just called reaction order. Okay, so I'm just going to explain this to you. It's a 1-to-1 proportion. So I guess I can write it down. As concentration doubles, now we don't have to set it up always like that. We could triple it. we could, and we don't have to look at the trials in order. So I'm actually looking at this. Maybe this is a little confusing. it does not matter that we don't have to look at trial 1 data, then trial 2 data. You can go in any order you want. Maybe it's easier to say, okay, going from trial 2 to trial 1, we double the concentration. Guess what happens? The rate doubles. So as concentration doubles, rate doubles. Well, what does that mean about the order of reaction? What proportional, what number there? And we're only going to consider 0, 1, and 2. By the way, these are called 0th order reactions, 1st order reactions, 2nd order reactions. Kind of makes sense. What does that mean? Well, that means that n equals 1. It's a direct 1-to-1 proportion. So our rate law, our rate law would be this. So this is when it says determine the rate law, this is what you would write. Rate equals K times H2O2 raised to the 1st power. This is a 1st order reaction, and I'm not going to do it here, but we could actually solve for K. And this is what we're going to do in the next problem. If rate constant is truly constant, you should be able to plug in a rate there, plug in a concentration there, and solve the equation for K. And it should be constant. So you solve for K for trial 1, solve for K for trial 2, and it should be about the same number. That's a double check. These problems are self-checking if you know what you're doing. And I'm not going to actually give you a number there. I just want to show you what the units would be. The units for the rate constant in this case, and you can figure this out, what would they be? So rate is molarity per hour. We're taking this concentration and only raising it to the 1st power, so the units are molarity. Well, I'll let you figure this out. The units on the rate constant here are going to be inverse hours. HR to the -1. I want you to figure that one out, okay? So that's a simple example. What I'd like to do is to actually, no, the next one is just not the same. And we're only going to do a single reactant example here. In class, we will do ones with more than one reactant. And you can look ahead in the book. If this makes sense to you and you want to go look at more complicated examples, you go ahead and do that. So 2, acetaldehyde decomposition. And my computer speakers are making kind of a weird noise. I'm going to turn them off. Sorry about that. All right, so this is also a single reactant reaction, homogeneous gas phase. It's basically the same idea as H2O2, but it's not the same problem. This is actually a really good contrasting example. Again, it doesn't really matter what the chemical reaction is right now. So this is acetaldehyde, and this decomposes into methane and carbon monoxide. This is a great example from your book. Go book. So here I'm going to give you 3 trials of data. Now I'll let you know here, if you have one chemical reactant, the minimum number of trials you need to do this problem would be 2. If you have 2 chemical reactants, the minimum trials you would need to determine the rate law would be 3, and I'll explain that later. So here, I'm actually giving you 3 trials, and so it's a little bit more complicated to look at. So let's go ahead and do this problem. I'm going to streamline this a little bit. So we have trial 1, 2, and 3. We go into the lab and we set up some initial concentration. And I'm going to make a change to my notes here, or from my notes. All of these are times 10 to the -3 in terms of molarity. So if they're all 10 to the -3, I'm going to put that up here in the units, just so the table is less complicated. That's a legit move. And then you would have to be given these data. You have to be given this whole table, by the way. I think we have a lab if we get to it this semester. Whoops. Initial rate is going to be molarity. And this reaction is pretty fast. That's molarity, capital M. Sorry, it looks sloppy. But you get it. You're used to it by now. So the trial 1 uses 1.75 times 10 to the minus third for the initial concentration. Then we do, oh, by the way, we do things logically. When you do this in the lab, you change the concentrations in some regular systematic fashion. Why would you not do that? It makes sense. Why would you increase it by 10%? Do it by something logical, like double it. And then maybe double it again. Or cut it in half, or whatever. But I don't want you to get locked into this that everything is always the same. Trials 1, 2, 3, initial double, double. Nah, it's not always that way. And the initial rates, I'm going to leave these are really small numbers because these are really small molarities, so the rates aren't that big. So I'm going to leave the exponential notation there. 2.06, so okay, it's good to talk it through. So the first trial, with a concentration of 1.75, the initial rate turns out to be 2.06 times 10 to the minus 11th molarity per second. This is the advantage of doing this over the book. The book just gives you the answers all at once without having to explain them. The second trial, you go back to the lab, you set up 3.50 times 10 to the minus 3 molarity, and you monitor it, and you get the initial rate as 8.24 times 10 to the minus 11. So what happened there? It didn't double, did it? What did it do? It didn't go up by a factor of 2. What factor did it go up by? All right, we'll get to that. And then we double it again. All right. So going from trial 1 to 3, it's increasing by a factor of like 7, but that's a little bit hard to interpret. Going from 2 to 3, we double it again. Well, what happens to the rate? 3.30. Whoa, went down? How's that possible? Well, it didn't go down because this is times 10 to the minus 10th. So it's kind of like comparing 8.24 to 33, if you will. So what happened there? You double the concentration again. What happens? Well, here's what happens, and this may take some time to figure out. Again, this is in your book, so if you don't like my explanation, go for it. You can go read it somewhere else. So how would you describe the relationship between concentration and rate? What would you say? Well, and again, we're not always doubling something. Maybe we'll triple it sometimes. If you double the concentration, that means that looks like the rate is going up by a factor of 4. So it's not 1 to 1. It's 1 to squared. So therefore, the rate is proportional to the acetaldehyde concentration squared. And then you make it an equality, and this would be the answer. And this is a differential rate law. The differential rate law would then be rate equals K times CH3CHO raised to the second power. So that would be the thing you put a box around or whatever. Got it? All right. So this is just get some vocabulary here. This would be a second order reaction. Fine. The units on K, which I don't know when we solve that. I don't know if we're going to do this or not. Oh yeah, I forgot here. Yeah, I actually am going to do that ozone example because yeah, it makes sense. This video is going to be a little long. I'm not going to do all of the ozone example, but it'll make sense. So then what we would do to finish this problem off, and we'll probably do this in class, is you would go back and for each trial, calculate a value for K. So you'd plug in for trial 1, you'd put, let's see, you'd put your rate here. you'd put the concentration of 1.75 here and square it. So that'd be like molarity squared. And then you would solve this equation for K, and K should be the same for everyone. So what I'll show you in class is you can actually set up a fourth column and calculate K's, and they should be constant. And then you take an average. So you take an average K. We're not doing that for this problem, though. All right? So the units, though, I just want you to rationalize this. The units here would be inverse molarity, inverse seconds. So guess what? If it's a second order reaction, those are the units of K. If it's it's inverse molarity, inverse concentration, and inverse time, whatever those units are, hours, seconds, days, years. For a first order reaction, the units are inverse time, hours, seconds, days, years, depending on what's used to measure it. Okay, that's example number 2. Example number 3, and I should just give you the option. If you're getting tired of the video, go to your book. Your book does this overall here. So I'm going to try to talk through this a little bit quickly, and we may end up, if this video is already at 20 minutes, we may just do the first part by inspection, and then I'll show you how to do the second part with math. I think that's a good option here. Let's just start this one, and then we'll finish it off in class, rather than try to have the videos do everything. That gets a little old. So the third one is the ozone depletion. You can write that if you want to. So this is slightly more complicated. We have 2 things happening, and this is a really good chemical reaction to discuss. I think a friend of mine from Rice University, who's an environmental chemist, who also contributed to this book, I went to high school with her, wrote this problem. So nitrogen monoxide, which is produced by a lot of impurities in fossil fuels, if that gets up into the upper atmosphere, it will react with the ozone, which is a molecule designed, or well, evolved, if you will, or produced to keep the ultraviolet light from coming through and hitting the Earth. And that produces NO2, which in and of itself is not very safe. It mixes with precipitation to give you acid rain, and then produces oxygen. So this is not a reaction we really want to have happen. Okay, so in this case, if you have 2 reactants, you need a minimum of 3 experiments. Now, our ultimate goal here, I'm gonna write this down here. Our ultimate goal is to determine the rate law. So we want rate equals K times NO raised to the N power, the order of reaction with respect to nitrogen monoxide, times the concentration of ozone with respect to, okay, you're going to want a number there, not just a placeholder. And then we will calculate K and take an average. And that's what we will write there. That's where we are headed, is to determine the average value of K, because it should be the same for every trial, the order of reaction with respect to N, the order of reaction with respect to nitrogen monoxide, the order of reaction with respect to ozone, and then N plus M is the overall order of reaction. That's where we're headed. That's what we want to determine here in this problem. So I'm going to erase this so I have plenty of space. Try to do this all on one. And I'll do this quickly. I just have to write down all this data. So there's 5 trials. Again, it's good to look at the data as it's being written down. So 1, 2, 3, 4, 5. That's more than is minimally required, but this will require you to think a little bit. We'll take the nitrogen monoxide, and I'm not sure if your book does this. These are actually molarities times 10 to the minus 6. So technically, these are called millimolar or millimolarity, but we're not going to put it that way. So the concentration here is 10 to the negative 6th molarity. Fortunately, we use the same units for ozone. And then initial rate. Oh, yeah, so what are we measuring here? Remember, it doesn't really matter what we use to measure initial rate. We just pick one of the chemicals that we have some instrument that can measure it. And NO2 is actually pretty easy to monitor. So you don't have to label this here, but you have to pick some chemical in order to monitor. So what is it based on? It's based on the nitrogen dioxide. If you want to write that down, it doesn't really matter because all the rates are tied together, as you know. And it's pretty fast, so it's per second. And actually, you know what? If you want to, put a column here for K. We don't know what the units are yet, because at the end, you should be able to calculate a K and get the same answer every single time because it's a rate constant if you do it right. Okay, here we go. So in the first 3 trials, the concentration of nitrogen monoxide is held constant. The 4th trial, it's doubled. In the 5th trial, it's relative to the first 3, tripled. Again, we're not doing the bare minimum. This requires you to do a little bit more. And ozone, we're starting out. Now, there's reasons why we don't just use the same concentrations. Oftentimes what you do is you have one concentration be much higher than the other so that the reaction is reasonably fast. So in this case, oh yeah, this equation's balanced, by the way. Isn't everything 1 to 1? Yeah. So to make the reaction go a little faster, we actually triple the ozone. Then we double the ozone. Then we go to, I guess, triple it based on the 3rd one. Okay, so make sure I have that right. Yeah, and here are your rates. Keep in mind the exponential notation. So the first one is probably not surprisingly the slowest because it has the lowest set of concentrations. So it's 6.60 times 10 to the minus 5th. The next one is 1.32 times 10 to the minus 4th. So the number looks smaller, but it's actually like comparing 6.6 to 13.2. Guess what? That's like doubling, isn't it? I'm giving it away. I shouldn't be doing that. Let me just write it down. You can think about it. Okay, I want to double check. 6.60, 10 to the negative 5th, 1.32, 1.98, 3.96, 5.94, all times 10 to the minus 4th. Okay, that kind of makes sense that trial 5 has the highest concentrations of everything. So based on our collision theory model of chemical reactions, that would make sense. It's the most concentrated. All right, so here we go. And we're almost approaching a half an hour. So we will there's 2 ways to do this problem. By inspection, which is a fancy way of saying just look at it like we did with the 2 previous examples, or mathematically, which we will do in class together. I'm not really overly concerned about that. I'm more concerned about the big picture here. So starting off, we have 2 reactants here. So the rate is going to be proportional. I probably don't need to keep doing that. To the concentration of the first reactant raised to some power called the order times the concentration of the second reactant. And we already kind of set our roadmap. Okay. Now, I'm not gonna write a lot here. You just kind of want to listen. Is the idea with these experiments when you have 2 or more reactants is you want to look at trials 2 at a time, and it doesn't have to be trials 1 and 2, 3 and 4, 4 and 5. You pick 2 trials that make sense, where you can interpret the data logically. What does that mean? This is classic experimental design. Hold one variable constant, do something systematic to the other variable, and see how it affects your outcome. And if that's, I don't mean to insult your intelligence here, but let's see. And you should get the same answer even if you don't do it the same way. So actually try it different ways from what we do. I think if we look at trials 1 and 2, that seems to make sense just right out of the gate. That won't always be the case. So in trials 1 and 2, the nitrogen monoxide is held constant and the concentration of ozone is doubled. What does that mean? Okay, well, we have to look at the rate, don't we? What happens to the rate? So we double ozone, and the rate, and if you're not sure what it does to the rate, just divide it. Divide the rate 2 by rate 1. What are you going to get? You're going to get 2. It doubles. So the order of reaction with respect to ozone, it's a 1-to-1 proportion. You double the concentration, you double the rate. Well, that's going to be 1. That's going to be first order with respect to ozone. And verify that somewhere else if you can. Maybe there's a better way of doing it. You could look at trials 2 and 3, couldn't you? But that's a little bit trickier because you're keeping the NO constant and you're taking the concentration of 6. Well, couldn't you look at trials 1 and 3? If you look at trial 1 and 3, the nitrogen monoxide is constant and the rate the concentration of ozone triples. Does the rate triple? I think it does. I think the rate triples. Well, so you should get the same answer. All right, take a second and see if you can figure out what nitrogen monoxide would be. So do the same thing. What will be some logical experiments there? Trials 3 and 4 look like they make sense to me. Ozone is held constant. It doesn't matter what it is. It doesn't have to be 1 or 2 or 3 or 5, just constant. So in trials 3 and 4, that's constant. And nitrogen monoxide doubles in trials 3 and 4. What happens to the rate? I think it doubles. I'm not really even looking at my notes here. Because actually I have in my notes, because we'd be doing this in class, we'd be doing this together. So it looks like that's also a 1. Okay, well that's pretty straightforward then. So the rate law would be the rate constant times nitrogen monoxide. And it's good to put the 1 explicitly so there's no ambiguity. And the overall order of reaction is 1 plus 1. So the overall order is 2. The order with respect to NO, nitrogen monoxide, is 1. The order with respect to ozone is also 1. Okay. And let's see. I don't think we need to do this. Yeah, I don't even have the answer. Yeah, I didn't even come through. Yeah, I didn't do the rate constants calculations because we would normally be doing that in class. So what you can do is go through on your own and do the calculation 5 times. Put in for each trial the concentrations raised to the first power. That's easy. Multiply those two, swing them over to the other side of the equation, divide the rate by those, and you should get the same K every single time. And guess what? It's overall a second order reaction, so the units should be, let's see, what's time here? Seconds. So the unit should be inverse molarity, inverse seconds, and it should be the same every single time. And we will do that in class. Preview of coming attractions, that's really what I'm going to expect you to be able to do, and probably nothing more complicated than 3 reactants. In fact, we have one more example, but then this video is going to be an hour. The other way to do this problem, it's a lot harder to do, but it's a good mathematical exercise, is you set up ratios of the rate laws, because K is equal to K is a constant, and you go through and you prove what N and M are mathematically rather than by inspection. I'm not going to harp on that too much. It's a very labor-intensive thing to do. Well, it's not that bad. Your book shows you how to do that if you want to do that on your own. But we will do that in class. So that's excellent. Long video. And we'll stop there. We are rolling now. Oh, yeah. Here's, you don't have to write this down. This is what we'll do in class. Well, this is what you should do for every one of these problems if you want an algorithm. Oh, okay. Yeah, sorry, this is not a generic algorithm. This is the one we're going to do in class. That's a little more complicated, so you can just ignore